I want to acknowledge as well that as I'm on the west coast of BC, I live on the traditional territory of the Coast Salish, Songhees, and WSÁNEĆ. I also want to give a thank you to the BMCA for the opportunity to share this workshop. This is my first Zoom workshop. I've done other live things before, but this is a little bit new, and everything is going to be live demos. So if this totally crashes and burns, then maybe I should have seen that coming, but hopefully things will go smoothly. So just a little bit about my 3D software journey. I started doing 3D animation with Maya in 2009. So a long time ago. I graduated from BMC in 2013, and I continued doing molecular animation in Maya until 2019, at which point I switched kind of cold turkey to Houdini. One day I was using Maya, and basically the next day I was using Houdini. So it was an uphill battle. It's not the easiest program to learn, but I've grown to really appreciate it and enjoy it for three main aspects, which I'll hopefully be able to give you a taste of today. So first off, data import and manipulation. So every good science visualization starts with data, and the easier that data is to work with, really, the better. Second thing would be procedural creation. So it may be a little bit hard to understand what procedural creation is without actually doing it yourself. But hopefully I'll be able to show you today how building a network of nodes, which will probably look scary at the beginning, but the idea being that you can have really cool, flexible workflows that you can reuse over and over in different situations. And third, tool development. So if you're going to be wanting to make reusable rigs, effects, assets, tools in 3D software, in a lot of applications, most of the time, you're really quickly going to be jumping into doing programming and all that sort of stuff. And of course, in Houdini, there is a lot of programming, and you can do a lot with that. But hopefully today, I'm going to be able to show you that you can build a really useful tool that you could use in different projects without a single line of code. So that's my promise, and we'll see if I'll be able to stick with that. So I'm going to start sharing my screen here. Hopefully this works okay. All right, I'm going to pull my chat window up here so that I can see if people are asking questions as well. All right, so this is my self-promotional sort of thing. So I shared a couple of files with you that I'll just paste Dropbox links in the chat here. So these are files to help kind of work alongside. If you're wanting to work alongside, I am going to go pretty quickly. So it may not make much sense to try and do it at the same time as me, but as you know, this is being recorded, so maybe you could follow along later, or just follow along in the example file and see what I'm doing. So what are we building? So what we're building here is an Actin Filament tool that basically the user can draw curves, any kind of curve or curves, and it's going to build actin filaments here. And we can change some parameters like the smoothness of the curve. Obviously, if you're drawing really sharp curves, Actin doesn't really do that. So maybe you want to have a little more smoothing to get something more realistic. We could change the surface resolution, so we could have low res. And then hopefully this doesn't chug too much because there are a lot of atoms. But if we change this to an atomic representation, you can see we have hundreds of thousands of individual atoms here as well. So we're going to be building all of that in like 30, 40 minutes. So we'll see how that goes. So like I said, if you open up the files that I've provided ahead of time, you might see something like this and a bunch of colored boxes. And those are just sort of organizational things. So I've created this final node network, which is what we're going to be making, alongside some empty boxes where I'm going to be filling it in live in this workshop. Okay, so maybe some of you have watched an introductory tutorial, and that's what I had up at the, we'll just go back to an introductory tutorial. If you're completely brand new to Houdini and you want a little bit more explanation about the hows and whys of how things work, I'm recommending that. I'm not going to be going into a ton of detail about why everything does what it does. So if you want more explanation, that's one place to go. Obviously, other tutorials are available. Okay, so diving in. So in Houdini, we have these sort of top level object nodes, which can contain any number of things, a whole bunch of stuff. So that's what we're doing here. Is this is kind of like a whole object, and we're diving in, and we can get into the nitty gritty of making geometry. Okay, and the way that I'm navigating in here is just middle mouse to pan and track, and the right mouse to scroll in and out, or the scroll wheel. So I'm going to be moving around, hopefully not too fast. Hopefully the camera or the screen sharing kind of keeps up with this and it doesn't look too much of a blur. Okay, so what are we going to start with? The first thing we want to do is get some data. And for Actin Filament, what I have is this PDB structure. And hopefully most of you are familiar with Protein Data Bank. You can download PDB files that have atomic coordinates for any number of proteins and different things like that. So this is the model for F-actin, filamentous actin, and we could download the file. But what I've created is a PDB file that has hydrogens. I use the Chimera X to add hydrogens to the PDB file. So I'm going to create a file node and just go to, I have it on my desktop here. So this is the 2ZWH PDB. And kind of incredibly, Houdini can import PDB files natively. I don't have to do anything to get that data in. So what you can see in the viewport here is a whole bunch of points. And it kind of looks like we're pretty much almost done with this structure. We've got all of the atomic data here. And if we look at the geometry spreadsheet, we don't have to do anything down here, but just for the sake of looking at what we have a whole bunch of point data, and each row represents a single point or a single atom. And the first three columns are the XYZ coordinates of that atom. And we have a whole bunch of other data that came in with the PDB file, element, residue name like asparagine or whatever that is, and a bunch of stuff. And the only thing that we're really concerned with today is the element. So nitrogen, carbon, carbon, oxygen, carbon, carbon, oxygen. That should look kind of familiar. Actually, one other thing that we might be interested in is at the very end here, we have this het atom group. And again, if you're familiar with some molecular data tools, het atom is an atom that's not part of like the main structure. So if in Houdini, a 0 means that that atom is not part of the group, and a 1 means it is part of the group. So if I just click on the column header, we can sort by het atom, and the ones that are part of that group, you can see here, are a calcium ion and ADP. And so that might make some sense. So we've got calcium and ADP, and the rest of it is just the protein structure. So just for simplicity's sake, I'm actually going to delete the het atom stuff, the ADP and the calcium, just because that's going to complicate things a little bit. So I'm going to use a blast node and blast away the het atoms, and that just deletes those. Okay. So the next thing we want to do is put some spheres on each of these points. So let's create a sphere. And the reason we want to do that is we're creating this space-filling atomic representation. So essentially, we're just copying a sphere to each of the points that we have this point data for. So I'm going to do copy to points. And the first input is asking what we want to copy. We want to copy the spheres. And the second input is the points that we want to copy to. Cool. Okay, we kind of have an atomic space-filling representation. But there's a couple things wrong with this so far. One of them is we don't have any color on there, which is really useful to see in this representation. And the second thing is the radius, the van der Waals radius that each of these atoms occupies. Okay, so I'm just gonna organize my notes a little bit here. So a nice feature of this copy to points is that not only does it copy the geometry to the points, but it can actually take these kind of attribute data, these are called attributes, this kind of data, to the spheres. And I'll show you an example of that by putting down a color node. And if I just do color random, you can see that it's applying a random color to each of the resulting spheres. Now, if you're not super familiar with these node network type of things, I'll just briefly explain that basically the way it works is that we kind of have a top to bottom flow of information. So the data that gets passed from node to node, so each node does a little operation and it passes the information to the next thing. So it's passing that point data to the color node, apply a random color, and then pass it to the copy to points and copy the sphere to each of those points. Okay, but we don't want to do random colors, obviously. We want to do something like a dark gray carbon atom. So for the group here, I'm going to say all the elements that are C, carbon, get a random color. No, we don't want a random color. We want something that's dark gray. So I'm just going to pick a dark gray color. Nothing happens here because we have to specify that this is point data. Okay, so now we've got dark gray carbon atoms and just default gray everything else. Okay, so the next thing we have to deal with is p-scale, which is a special attribute that Houdini uses to scale, to kind of hold scale information. So I'm going to actually create something called an attribute create to specifically create that scaling attribute. And this is all going to look like mysterious magic until you kind of get used to some of these inbuilt keywords. And I'm going to copy that same element C group, and this is point data. And we want the value for carbon is 1.7 angstroms. That's the van der Waals radius. Now, what happened to the rest of our stuff? It got scaled basically down to 0. And that's because when something is not in this group, it's going to use the default value. So that's okay. We'll deal with that later. But I might just want to put something in here like 0.5 to see that there's stuff that we still have to deal with. All right. So now we've dealt with the carbon color and scale. Now we want to do the same thing with oxygen. Just pop that in there. Nitrogen, sulfur, and hydrogen. So just pop these in series here. And this looks a little bit sort of inelegant because there are maybe better ways of doing this, but I promised that I wasn't going to do any coding. So I'm just going to kind of do a little bit of manual stuff. So nitrogen is 1.55. There we go. So we've dealt with nitrogen. And then if the element is O, that means it's oxygen. Some red color. Choose your own pretty colors. Although these ones are kind of conventional. Sulfur is yellowish, something like that. And again, I'm kind of going through this sort of quickly, but hopefully the gist of what I'm doing is becoming apparent. So we're creating this atomic representation 1.2 for hydrogen. Whoops. Seems I forgot to put some of these. This one was sulfur. And that one was oxygen. Okay. Nitrogen, oxygen, sulfur, and hydrogen. All right. And there we have it. We've got an atomic space filling representation for our PDB data. And the cool thing about this procedural workflow is we could put any PDB file in there and we would pretty much get a correct atomic representation of that. And so you could package this up, and indeed I have, into a little atomic representation tool. But we're going to go even further. So I'm going to put down a null, which is just kind of like this bookmark. It's just another sort of organizational thing to help us navigate our network here. So that's going to be atoms. And next we're going to do a surface representation. How's everybody doing so far? I've made all of my gallery view and everything invisible, so I can't really see any feedback, but if someone wants to give me a thumbs up in the chat or something like that to to let us know whether we're doing okay. I know I'm going quickly. So a surface representation, how we can do that. All right, looks good. Is using a node called particle fluid surface, which sounds pretty complicated. Whoops, and don't dive in there because it'll look really complicated. But this, you might kind of guess what this is going to do. So I'm just going to split off from the original point data. And actually, I'm just going to put a null. Whoops, not there. Put it here. And I'm going to call this point data. And I'm going to split our network here. So this is kind of our master point data. I can put the display flag on there and always just show, I can put the display flag on any node in the network and see the result of that node. So this is our point data. And we're going to apply this particle fluid surface node, which isn't going to do anything at the beginning because we need to put in some parameters. And the ones that I ended up using, let's do two different resolutions. We can do a low res and a high res like I showed at the beginning. So let's start with the low res. For the particle separation, I'm going to do 1.4, voxel scale 1, and then the ISO value of 1.8. These look like magic numbers because I just kind of played around with them until I got something that looked okay. Now this doesn't look particularly low res. I'm going to put down a remesh, which does this sort of procedural remeshing process. Oh, and the other thing I want to do here is instead of surface polygon soup, surface polygons, which is just more regular geometry. Polygon soup is a special kind of data type. All right, so that's going to take a little bit of time, probably because, yeah.
There's a question in the chat. Sorry if I can jump in.
Yeah.
So
yes, you can save the atom attributes for future use. And so I'll show you sort of towards the end of this workshop how to kind of package up node networks. So you can package up any kind of processes or operations as kind of little packages that you can use in a variety of circumstances. So yeah, definitely. So I accidentally set the target size way tiny, so I remesh this into an ultra high res. Okay, so that's more low res. I'm going to do 3 iterations and a little bit of smoothing and turn off don't compute normals. And there we go. There's a nice chunky low res sort of actin monomer. All right, so I'm going to take these two nodes and copy and paste them over here and make my high res version. So high res, I'm going to do particle separation of 0.7, voxel scale of 0.6, just sort of a more higher resolution thing, droplet scale 1.3, and an ISO value of 0.7. Do we get something here? Yeah, and then a remesh, we want to remesh to something like 1. This is sort of like the edge length that it's trying to get to. I'm going to reduce the smoothing a bit, or the iterations. Okay, there we go. So now we've got a high res actin monomer and a low res actin monomer. And in our tool, we might want to switch between these. So I'm going to put down a switch node, which is going to allow us to easily, if I put the display flag on that, switch between low and high. And once this has sort of been calculated once, it might take a little bit of time when you first open your scene, but then it kind of gets cached and it's very quick to kind of switch between those because it's already sort of calculated that. Cool. And that's our surface representation. Surface, if you can see that there. Hopefully the text is showing up okay on camera. And in our tool, we might want to switch between these atoms and surface. So I'm going to put down another switch node and switch between atom and surface. And again, maybe you want to have a tool that allows you to have both and, but for simplicity's sake, I'm just going to have sort of an either or scenario here. All right. So the next thing we want to do, if there's any questions, feel free to drop them in the chat and I'll try to answer as I go along, or hopefully there'll be a bit of time at the end as well to answer questions. So I'm just going to jump into now that we've kind of made this molecular visualization tool. Obviously, this is not as full featured as Molecular Maya or EPMV yet, but I've only spent, a little bit of time on it, and already it's, reasonably capable. Again, you can put any PDB file up at the top and you can get some kind of surface or atom things. And there may be some special cases that you have to deal with, but this is a pretty versatile and useful network already. All right, so now we want to duplicate our actin monomer a bunch of times. I'm going to use the surface representation for now. So for test purposes, we're just going to start by copying it up in a straight line. And then we're going to deal with applying it to a curve a little bit later on. All right, so to start, we kind of want to package up this geometry into what Houdini considers a single unit. You can think of it kind of like instancing, or kind of instance to particles, or a special kind of duplication process. But in Houdini, it's a special pack node that turns this into a packed primitive, so that it kind of treats it just like a single entity of geometry. You can see in our spreadsheet, we just have one point essentially. And what I want to do is copy and transform it. So this is kind of like your duplicate special, or that sort of functionality. Let's make 10 copies here, something like that to start out with, just so we can see how this is working. And how do we want to copy this? Well, we want to copy it in Y. We're just going to copy our monomer straight up. And I had to look up some of the data on actin filaments, but it turns out that a translate of 27.6 angstroms is the spacing between monomers, and they're actually rotated relative to the previous monomer, negative 166.6 degrees. Okay, so you might look at that and say, okay, that looks kind of reasonable for an actin filament, and it seems like a decent start, but this is actually not quite correct in terms of how the monomers are located next to each other. And the reason is we have to transform our initial monomer in a specific way so that it kind of lines up. And the way that I did this was I grabbed another PDB file that had a biological assembly of like 5 actin units. And I sort of copied that and sort of positioned everything so that it kind of matched that existing template. And the way that I'm going to do it here is I'm going to put, actually, get rid of this null here, a transform right up at the top. And the cool thing about working in Houdini in this sort of non-linear way is that you can add stuff higher up in the network without breaking everything and without having to go back and redo steps. So for example, we can put this transform and move the point data around before any of the other operations happen. So what I found worked and looked sort of accurate is to put to translate the pivot so that the rotation happens around the proper point. So something like 20.5, 0.3, and 2.9. Again, magic numbers, but I kind of played around with this until it matched my template. And then translate negative 38.9, and you can see it updating in the viewport here. Negative 28.2 in Y, and sorry, no, that's 0.4 in Y, and 5.1. And the file that I gave you has these same nodes with the same values. And in rotation, 90.5, negative 28.2, and negative 184. Okay, so now theoretically, that's a much more accurate actin filament. And you might believe me or you may not. That's okay. There's probably room to finesse this a little bit more. Okay, so now we've got that high res version, and we can see that that looks at least plausible. Okay, so now that we've got this sort of copy here, and we can make, endless copies of that, however many we want, we actually want to do this along a curve instead of just along a straight line. All right, so with our tool, we kind of want to have the user provide an input curve, whatever curve or set of curves that they want to use for that, because that's what would be useful in the scene, right? You don't just want a static actin filament, you might want to have a curve that, that fits with your molecular environment. But just so that we have something to work with, I'm going to put down a curve node here. And in the viewport, I'm just going to click and create this sort of zigzaggy curve. Now, if we try to put the actin filament along this curve, it's going to look totally bad because actin filaments, as far as I know, don't have sharp corners. So we might want to process this curve a little bit. So I'm going to do that by doing a resample. And the resample node just changes how many points are along the curve. And I've actually hidden some of the interface in Houdini here, just to give myself a little bit more space to work with so that the UI can be a little bit bigger for visibility. But I can turn on a point display so we can see how finely grained those points are. That's not what we want. We want something like a 200 unit spacing between them. And I'm also going to treat them as subdivision curves, not as straight edges, so that we get kind of this smooth curving. So here's our original curve, and here's our resampled curve. And speaking of smoothing, we might actually want to even smooth it further. So we could put down a smooth node. And maybe reduce the filter quality so it kind of just really smooths that out. Now, I don't have data. You could look up data on the sort of the minimum radius of curvature of actin filaments and try to calculate how to get the curve smooth enough so they're not bending too much. That would be unrealistic. But for this case, I'm just kind of eyeballing it to smooth things out. But you can have your user sort of play around with that on a case-by-case basis. So we're going to expose these sorts of settings. All right, and then for the actual placing that monomer along the curve, we want to resample it again. And this time, the distance between the points, we want exactly the same as our copy distance, 27.6 angstroms between units. So we'll put that in there, 27.615, because I had more precision in my notes. And one little thing to uncheck, if we look at the end of the curve here, this is a long setting. Even last segment, same length, is a confusing setting, but basically it just means we're okay to crop the curve so long as we keep each of the sort of the edge segments exactly this value instead of sort of evening them out to some slightly different value. So anyway, don't worry about that too much. It's just works out better. So treating polygons as subdivision curves as well, so that we get even smoother. And now we've got a nice smooth curve that we can copy our packed actin monomer units to. So we've got our actin monomer geometry here, and we're going to put down a copy to curves, sensibly named. We're going to copy that geometry, and we're going to input the curve that we want to copy it to. Bam. Okay, so now we've got this monomer copied along the curve, but obviously the rotation is incorrect. So let's fix that here. So I'm going to scroll down in the settings here, and under additional rotations, we're going to apply some roll or twist. And we check that and we get a bunch more options. And I'm going to go into partial twist, and I'm going to go negative 166.6. Again, that's the same rotation that we had on our original sort of test, negative 166.6 degrees per unit. So now what this is doing is rotating along the whole curve. That's not what we want. We want for every single sort of segment or point, we want it to rotate by that amount. So we're going to twist per edge. I like how they put per twice, so you really know it's per. Twist per edge. And there we go. That looks correct, but it's actually not correct. So what's happening here is instead of with this copy to points, the copy and transform, we're copying this monomer up in Y. the copy to curves actually expects the sort of the up direction to be the Z axis, which I think is in here somewhere. But to fix that, I'm just going to put down a transform node here and rotate the x-axis 90 degrees. And now we have it actually in the correct axis. And I had to prove that to myself. I made this little debug tube. I can show you how that works. So I just created this little cylinder, merged it with my geometry like so. So I said, this is the axis that I want the filament to go along, because I knew that was correct. And then in here, you can't really see it unless I zoom right in, but you can see that that tube is hidden in there going along the right axis. And if I didn't have this transform, then you can see the tube is sticking off perpendicular to the curve, which is not right. Yeah. So again, when you're doing, this is sort of like inside secret, when I'm doing molecular visualization and I'm trying to match some kind of template, I find the best representation to match stuff with visually is the backbone representation. So, you know, those cartoon squiggles, the ribbons, essentially. If you can have, and I've set up a little tool for myself to create a ribbon representation. If you have ribbon and ribbon, it's so much easier to line those up because you can see where the alpha helices are. You can see kind of the space. It gives you more breathing room to actually like see inside the structures. That's really the best way to sort of line things up with the template and make sure that you don't have domains intersecting with each other and stuff. Because like it is here, it's kind of hard to say whether or not that's actually accurate. So, all right, so I'll just hide that tube there. All right, and we're basically done with our actin filament. So I'll save that. Just think if there was anything else in that section. Again, I know I'm moving quickly, but I want to cover the whole set of stuff. So this actin filament, this is real geometry. You could do so much with this. You could have your curve and have like a hair simulation or wire simulation so that your actin filament is waving and bending. You could treat each of these monomers as a rigid body and have this rigid body simulation where monomers are floating around and they're assembling as the actin filament is polymerizing. That would be a bit more of a complex effect, but definitely doable. Yeah, so, and you could export this model to Maya, Cinema 4D, Blender, whatever you want if you had your scene going on there. So you could have certain assets built in Houdini and then exported. There's a lot of flexibility with this here. So to finish up with this tool, what I actually want to do is wrap this into what's called an HDA, or short for Houdini Digital Asset. And that's kind of this package that you can use in many different scenes. So it's not tied to this one particular file. You could share it with people. You can have Houdini has something called a Houdini engine so that you can bring these digital assets into other applications like Maya, Unity, and Unreal, which is pretty cool. I haven't played around with that too much, but that's a neat idea. So basically, we want to get everything except for this input curve. So I'm going to bring the input curve out over to the side and then select everything else. And I'm going to select this cardboard box icon, which is going to collapse everything into a black hole, or rather into a subnetwork. And if we double click on that subnetwork, we can see we have all of our work still inside there. But this subnetwork, we can then turn into a digital asset. So I'm going to right click and choose Create Digital Asset. And we can call this Actin Filament. I'm just going to add workshop. So I know this is the one that I made in the workshop. And we can give it a label, Actin Filament. And this is going to get saved in your documents folder under Houdini, under a subfolder called OTLs, which is the old name for HDAs. Anyways, it's an HDA. LC is short for limited commercial because that's the license that I have, the Indie license, which is very affordable. Okay, so that's going to basically take all of that network data and save it out as a separate file on disk. So it's not living in the scene anymore. It's kind of this separate thing, which makes it usable in all your different scenes. And now in the parameters view, we kind of want to create a little settings panel. And it's very easy to create settings or parameters for your digital asset. We can click on the parameters tab and basically just drag and drop what we want in here. So the first thing we might want is switching between different representations. So I'll just drag that in there. Let's expand this out a bit so you can see here and label that. Let's call it representation. And then we want to switch between our low and our high and our low. So we'll call this surface resolution, something like that. What else do we want to do? We want to control the smoothing. So I'll just grab the smoothing strength and the filter quality, and I'll call this smooth strength for our curves, and whoops, smooth filter quality, something like that. Anything else? I think that's good. So I'll hit apply and jump up here. And now we can see, actually gonna hit accept. I can always bring this back up. Now we can see in our tool, we've got some different sliders. So we've got the representation. So again, I don't want to make this chug too much, but we can switch to atomic. And just a side note, these colors are actually incorrect in the viewport. It does a funny thing with the point numbers and the colors that are associated with them. But if you render it, it's fine. So we've got surface and atomic, and we can change the to a high resolution. That's just going to calculate because this is sort of the first time it's cooked this network. And then the smooth strength of the curve, we could, so smoothing out the curve. You can see this is very responsive. It's a very fast network at this point. So it's very easy to work with. And actually, just for some quality of life, I'm going to change the type properties. So that's changing the digital asset parameters. For the representation, I'm going to change this just from a slider into a drop-down menu, because drop-down menus are way nicer to work with. So for a value of 0, that was the atoms. A value of 1, that was the surface. I'm going to apply there. So we've got surface and atoms, cool. And then the resolution, I'm also going to change that to an ordered menu, and do 0 was low, 1 was high. There we go. That's nicer. Atoms, surface, low, high. So you can see it's fairly quick and easy to make a usable interface for your custom tool that you've just created. And I'm just going to do save node type because this is, again, it's a separate file. It's not, it's saved on disk elsewhere. So you have to save that separately. I'm going to do match current definition. That kind of locks your asset so that people don't actually accidentally change it. And instead of this curve, we could do something different, like using the stroke. I'm going to plug in the stroke here. So stroke allows you to just draw curves, and those curves go into our Houdini asset and create actin filaments. And again, we can go there, change the smoothing, change to a high resolution surface representation. Take a little bit of time to calculate. And there we've got high res actin filaments. And of course, you could do something cool and complicated, like doing a level of LOD, level of detail based on the distance from your camera or something like that. Lots of different things you could, lots of different directions you could take this. One final note, and then I'll take questions. You'll remember that we had this actin PDB data. And so what you might want to do in a scenario like this is kind of a little bit advanced, but not too bad, is you can actually package files with a digital asset. So you wouldn't necessarily want to assume that whoever's using this tool, or whenever you're using this tool, that file's in the same place on somebody's hard drive. So you might want to bring that with you. So I'm just going to grab this. It's living on my desktop right now. Go to extra files, put in the file name there, do add file, apply, accept. So now that's saving that PDB file in the digital asset as well. And then what we do on this file node here is, instead of pointing to a path, we do something that looks kind of scary. Opdef : ... And that is basically saying access this special extra file within the HDA itself. And of course, I had to look that up, what that's in the documentation. Anyways, so that's kind of the last thing that you would want to do before making this a portable tool that you could share with your friend, or just keep it to yourself, because, you know, this is secret sauce. This is how to do cool things, and we don't want to share those secrets with anybody, do we? Oh, I'm doing a workshop. I guess I do want to share this stuff. Okay. So yeah, that's pretty much it for me. I think we have a few minutes for questions. If I haven't lost everybody completely.
I have a question.
Yeah.
I don't know if we're supposed to formally raise our hands. Sorry.
No, go ahead.
Oh,
I'm not sure who's talking because I
sorry.
don't have the thumbnails up here, but
I'm just curious because, you know, there's so many different kinds of nodes, and it can be, you know, for someone just starting, you don't know what kind of nodes to use, obviously. So I'm just wondering, like, when you were learning how to use Houdini, did you just pick that up through watching tutorials, or do you have any tips for getting familiarized with the different kind of nodes that are available?
yeah, that's probably one of the biggest challenges, especially because a lot of the time nodes will do different, like a variety of different things. And the thing that you're actually wanting is sort of this secondary function of a node that's named something completely unexpected, like add or frame or, you know, poly split or something. It does like all these extra things. It's just a lot of Googling, like, how do I do this? How do I do that? And people will, there's lots of, like, there's good communities out there, good Discord channels or Discord communities and Slack and forums and everything like that. So getting hooked into those sorts of things. There's Matt Estella has a good site called CG Wiki, which has a whole bunch of great not video tutorials, but little like snippets. Yeah, CG Wiki is great. That's really good for looking up examples of doing a variety of things. And it really is just time and practice, really, that you sort of start to slowly build up your repertoire of what tools and nodes are available. So there's, I can't say there's any like secret shortcut to learning a variety of nodes, but and I know that even the most experienced Houdini users, like somebody else will do something, they'll be like, oh, I didn't know that that node, you know, does such and such, and you could use it for that sort of thing. So yeah, it's just, yeah, taking time and lots of Googling. Do you run into viewport lag issues when adding adjusting nodes towards the top of the workflow? I imagine with more complicated setups, this might cause live viewport issues. Yeah, so it depends on how long it takes your network. The term they use is cook, so cooking the network. So yes, you do, and I find, like, when I'm working, I'm not working in the viewport as much as I'm working in the node network. And I think you probably saw that as I was working today. I'm not really doing very much in the viewport. So sometimes, yeah, you have to wait a few seconds for it to catch up. Sometimes it's as much as minutes, especially if you're doing like a simulation. So you just kind of have to tailor your expectations for how responsive things are going to be based on the type of work you're doing. So sometimes you do something extraordinarily complicated and you go for lunch and you come back and you see what happened. Or maybe you get something that's actually works very performative, like this Actin Filament tool seems to be pretty good. You can just draw strokes and it kind of updates immediately.
We've got a couple of questions earlier in the chat. So Jen asked, if you wanted, for example, one strand different, would you create a separate tool or set of attributes, or how would you edit that?
Yeah, so one strand different. So for example, you can make any number of copies of this, right? So I could have the same stroke going into, I'm just gonna remove some of these so it's not, so I've got one stroke here. So we've got one version that could have the high res and one version that could have the low res. And you can kind of have some settings on one and some settings on the other, and then you can merge them back together. So, and obviously you could have different things going into different. So here I've got two different, so a stroke going into this copy of our tool and this curve going into this copy of our tool. And we've got low res here and high res here. So hopefully that gives you an example of how that can happen.
Yeah.
Mentioning, yeah, so exporting to programs like Maya usually render straight from Houdini. So I render in Houdini using Redshift. Redshift is great to work with in Houdini, and I recommend it. Obviously it's an extra license that you have to pay for, but that's what I opt for. I haven't been using Maya. I do still think that Maya has value in addition to Houdini. So if you could afford having both licenses and using the strengths of one versus the strengths of the other, that's one way to go. And so you could, just mix and match. So, and that leads into Avesta's question, what made me decide to leave Maya cold turkey and go to Houdini? Honestly, at that point, it was cost, because I was starting freelance. Well, one of the reasons was cost. So Maya didn't have its indie license at that point. So I would have had to pay like $3,000 or $4,000 or whatever it is dollars per year to stick with Maya. And Houdini has the indie license, which is around $300 per year. So a 10 times difference in software cost is quite a big thing. And I also was really interested in the procedural nature of Houdini and the powerful things that it can do. So I did not try playing with other procedural tools. I do know that there are. So Maya has some procedural stuff. Obviously, it's got its own node network, and it has some more Bifrost tools as well. And Blender is developing in that direction as well with its geometry nodes. I haven't really played around with those. I think Houdini's been in this game the longest. And so I think it really shines there. But there's definitely it's not to say that Houdini is the only place where you can do procedural tools. Obviously, you can do some things in other programs, and sometimes that's it's best to stick with those. So there's value in learning that kind of way of working as well too. Hopefully that answers your question.
All right, any other questions? Now's the chance. You get to get every last drop of the secret sauce that Stuart's sharing tonight.
What are the cons, if any? So where Houdini is less effective is sort of the direct artistic manipulation of what you're trying to create. So if you're trying to sculpt some like muscles or anatomy or a person or a character, something like that, Houdini's not the best place to go. I mean, I would go to ZBrush for something like that. So ZBrush and Houdini are kind of sitting on opposite ends of the spectrum in terms of like direct manipulation of your stuff. And Houdini is sort of like setting up these rules and procedures and operations to generate something. So both of them are very flexible and powerful, but they kind of are different ways of working. The rigging tool set and the animation tool set in Houdini in some ways leave something to be desired, but just in this most recent 18.5 release, they've started a new sort of paradigm of rigging called KineFX, which is really cool. And I've played with that a little bit. And I think that's a nice direction that they're going to kind of really harness procedural workflows for rigging. But traditionally, Maya is kind of like the king of animation, like keyframe animation, character animation as well. But I find like in science visualization, so much of the time you are dealing with things like rules, and I know rules is kind of a strange way to put it, but if you think about like how molecules like are structured and how they interact and how cells are constructed, they're very sort of like non-specific in a way. Like you don't have like just one quintessential cell, right? They're like, if you have a field of cells, they're all slightly different shaped, and they're squashed and they're stretched and they're stuck together and they're interacting, and things move in blobby ways and stick out projections, and filaments wiggle and grow and shrink, and all those sorts of things. I think Houdini really, like, it kind of works really well together, because you're setting up not one specific entity, but you're setting up systems for how things are constructed, which I think is really cool. And it really helps you think about the molecular systems in a cool way as well. All right, so I'll stop sharing my screen here.
All right, well, we are at the hour. We can stick around for another couple of minutes if anyone else has any questions, but Stuart, thank you so much for everything you've shared today. It's really, really fascinating, really exciting. And as we mentioned, we are recording right now, so we'll make this video available afterwards. We will follow up with these additional resources and everything, so keep your eyes out for that. And yeah, thanks again, Stuart. This was great.
Oh, my pleasure. Thank you.